Go. We're going to start off with a review of what you did in Algebra 1. So I'm going to take you nicely through it so that, Angelo, you were right over there. Yeah, we do new seats every quarter. All right, exponential functions are functions made of exponential expressions where the base is a constant and the exponent is a variable. So go ahead and highlight that piece right there. An exponential function has the exponent is the variable. So I have a question for you. Which is the exponential function? Is it f of x equals x squared? Or is it g of x equals 2 to the x? Which one is the exponential? Yeah. Yes, g of x equals 2 to the x because the exponent is the variable. So we're going to do a little investigation here. And we are going to look at 2 to the x. And that's called a parent function. And here's the good news. We're going to go back through all of those transformations. We're going to start those tomorrow, and we're going to go nice and slowly through this topic. All right. If I want to graph g of x equals 2 to the x, are there any issues if I plug in a negative number in for x? No. Is there a problem if I plug in 0? No. Is there a problem if I plug in positive numbers? One of the questions I heard as we were doing parent functions is, how do you know your tables? Well, if you have a square root, you can't put negatives underneath. And one that we haven't looked at yet is a fraction. Like if I divide by a variable in the denominator or bottom of a fraction, I can't divide by 0. So your tables are going to start with negative 2 to 2 unless you have a restriction on that domain. So a couple things I want to refresh your memory back from Algebra 1. In general, what's a to the 0 power? What do we remember? Anything to the 0 power. Is it 0? No. What is it? It's 1, right? It's 1. The other one we need to remember from Algebra 1 is the negative exponent property that says this. A to the negative n is 1 over a to the n power. These are two pieces of information you're supposed to remember from Algebra 1. So, in my table, I'm going to take 2 to the 2, that's 4. 2 to the 1 is 2. 2 to the 0 is 1. And now watch. If I want 2 to the negative 1 power, that's 1 over 2 to the first. That's 1 over 2. If I want 2 to the negative 2 power, that's 1 over 2 squared. So that's 1 over 4. So my domain is negative infinity to infinity for all exponential functions. Remember that for the v's? The v shape was negative infinity to infinity for my domain. My u's, negative infinity to infinity for all parabolas that open up or down. So 2 to the x. Any exponential will have that domain. Before I state the range, let's go ahead and plot these. Here's 2, 4, 1, 2, 0, 1. And if you remember from Algebra 1, an exponential function gets closer and closer to the x-axis but doesn't touch it. And that leads me to a definition I have below called a horizontal asymptote. There is a horizontal line that as x goes out to negative infinity on this one, as I move to the left, it's going to get closer and closer to this horizontal line without touching it. So my range is actually 0 to infinity. It's not going to touch the x-axis as x goes to negative infinity. That's far to the left. My y-intercept is in my table. It's 0, 1. And then guess what? There's no x-intercept. This will not touch the x-axis. And then there is an asymptote. It's a horizontal line of the x-axis, and we call it y equals 0. So this is a parent function, g of x equals 2 to the x power. So let me talk you through everything one more time to make sure you heard everything. The domain of all exponential functions is negative infinity to infinity. Now, the only time my range is going to change from 0 to infinity is when I shift this up or down, which we're not going to do that today, but tomorrow we will do the shifts. My y-intercept is where x is 0. So you plug in x is 0 and get the y value. Now, unless I shift this up or down, I won't have an x-intercept. And then my asymptote is actually a horizontal asymptote. And let's go ahead and tie this together with the definition here. A horizontal asymptote is a line that the graph approaches as x approaches infinity or negative infinity. And we write that like this. X with an arrow, infinity, or x approaches negative infinity. If you're going on to pre-calculus next year, you will look at much more complicated graphs where a graph can cross a horizontal asymptote in the middle, like around the origin, but it never ever crosses as you go far to the right or far to the left, okay? End behavior is another way to describe the horizontal asymptote. It's what's happening as x approaches infinity or x approaches negative infinity. So anytime you're asked for end behavior, that's the horizontal asymptote. Note, exponential functions are continuous functions. I can draw them without lifting my pencil, and they're either growth or decay. So in this investigation, this one demonstrates growth. When I look at the graph from left to right, it rises. So that's growth. All right, let's continue the investigation. And I changed the parent function to f of x equals 1/2 to the x power. So my domain, again, is negative infinity to infinity. When your domain is negative infinity to infinity, your table should go negative 2 to 2. So let's start at the bottom. I like to start where I know something. If I take 1/2 and I square it, that means 1/2 times 1/2, which is 1/4. If I take 1/2 to the first, that's just 1/2. If I take 1/2 to the 0 power, what's anything to the 0 power? It's just 1. Now, here's the tricky part. When you have a fraction to a negative exponent, when you have a fraction to a negative exponent, it flips the fraction and makes it positive. So that's just 2. And if I take 1/2 to the negative 2, it flips the fraction and makes it a positive 2. Well, 2 over 1 is 2, so 2 squared is 4. Let's go ahead and plot this. So I have negative 2, 4, negative 1, 2, 0, 1, then 1 comma 1/2. Now when you're drawing your graph, make sure the graph does not touch the x-axis, and then draw a dashed line. Okay, the horizontal asymptote is a required piece. It is required on the graph, on your sketch. So my range didn't change. It's still 0 to infinity. My y-intercept is still 0, 1. There's no x-intercept. And the horizontal asymptote is still y equals 0. And it does have to be an equation, y equals. Notice that this graph shows decay. Decay means the graph is falling rapidly from left to right. Is this coming back to you from Algebra 1? So some yeses, some nos. Okay. That's okay, because I'm teaching it like you've never seen it before. So does it make sense what we've done? Just plotting the points. So this is what the general form of an exponential graph is. Yeah. Great question. Okay, for my range, it never touches 0. That's why it's a parenthesis. Now, when I'm talking about my x-intercept, that's not interval notation. That's the point 0, 1. Points don't have brackets. Okay? But great question. My range, there's no bracket around 0 because that would mean it's touching the x-axis, and it doesn't touch it. It gets closer and closer and closer, but it doesn't touch. Okay? All right, so let's look at some applications. Like, who cares? Who wants to look at an exponential function? Well, you use them in a lot of places in the real world. Money, if you invest money or put money in your savings account, that is exponential. Yeah, you can look at bacteria growth is exponential. Lots of different possibilities of where you see these. So let's look at example 2 together. Most automobiles depreciate as they get older. Suppose an automobile that originally cost $14,000 depreciates by 1/5 of its value every year. So if you depreciate by 1/5, that's 0.2, which is 20%. Well, we call R the rate, and if it is depreciating, it's going down by 20%. So you're paying, or it's worth, 80% of its value each year. Again, the automobile depreciates by 1/5 of its value each year. So if it's depreciating 20%, it's keeping 80% of its value. So watch what I can do. I can actually write an equation that looks like this. Y equals 14,000 is the value of the car, and it's going to be worth 80% each year, and I'm going to call the years t. This is exponential. So if you have a calculator, I would grab it. It says, what is the value of this automobile after 2.5 years? So we're going to plug in the time is 2.5. So let's make sure you know how to do this on your calculators. On the graphing calculator, you have a little caret button. This is the caret key on the graphing calculator. So you can press the caret to get to the exponent. On a standard scientific, it usually looks like this, y to the x button. So plugging this in, I got $8,014, and money is rounded to the nearest cent. So I would say in 7 cents. All right, part B. When is this automobile worth half of its initial value? Well, what is half of the initial value? $7,000. So what we're going to do is we're going to replace y with 7,000. And I want you to notice that the question asked when. When represents the time. Now we need to review PEMDAS. I cannot multiply before the exponent. So I cannot do 14,000 times 0.8 to the t. That does not follow order of operations. So what I can do, though, is as I am trying to solve for t, I can, in fact, divide by 14,000 and get 0.5 equals 0.8 to the t power. So we don't know how to do this yet algebraically, but we are going to learn how to do this in this chapter. So what I want you to do, though, is either on your graphing calculator, or we can pull up Desmos. Let me show you how we solve this. Like, we have a technology tool. So watch, I'm going to pull up my Desmos. And I'm going to type in y equals 0.8 to the x. And then I'm going to do y equals 0.5. Okay, it's like plotting the left side and then the right side. So the right side was 0.8, and you could have used the letter t, would be fine. And then look, this is at 3.106. On the graphing calculator, okay, if you're using the graphing calculator, you press menu and then analyze, I think is number 6, and you should see intersect. But for our purposes, t is about 3.1 years. That's not very long, is it, to go half the initial value? All right, the half-life of the value of the automobile is the amount of time needed for the value to decrease to half the original amount. All right, so in the box here, an exponential function is of the type y equals a times b to the x. A is called the y-intercept, and b is the growth rate. Exponential growth and decay are both modeled with this general form. Growth is modeled by a base greater than 1. Decay is modeled by a base that's less than 1 but greater than 0. In general, a larger base models faster growth, and a base closer to 0 models faster decay. All exponential growth curves have a doubling time, just as decay has a half-life. So let's look at example 3. Identify each function as growth or decay, and then what is the y-intercept? So here's what I want you to write down. We're going to write down a couple of things. If I have y equals a times b to the x, if b is greater than 1, it's growth. If b is a number between 0 and 1, it's decay. To find the y-intercept, you let x equal 0. I strongly recommend that you read through your notes before you start doing homework, because you're not supposed to be able to just have everything stick in your brain after we go through it once. You should read through the notes today, read through the notes tomorrow, read through the notes again before we take the quiz, and then you'll get a little bit more every time you read through it. Okay? So, in example 3, letter A, y equals 12 times 0.95 to the x. What is B in this problem? What number is the B? Good job. It's the 0.95. Now look at what we wrote down. Is B growth or decay then? It's decay. Good job. Because the B value is less than 1 and greater than 0. Now it says find the y-intercept. Well, in order to find a y-intercept, you let x be 0. Well, it's a good thing we reviewed this. What's anything to the 0 power? 1. So y is 12. The y-intercept is 12. That means it's 0, 12 on the y-axis. All right, letter B. What is B in this one? 2. Is that growth or decay? It's growth. In order to do the y-intercept, you let x be 0. Well, 2 to the 0 is 1, so my y-intercept is 0.25. All right, so in order to determine growth or decay, you identify your B value. The B value tells you growth or decay. To find a y-intercept, you let x be 0. All right, example 4. Evaluate f of x equals 3 times 2 to the x when x is 4. All right, well, we're going to make a beautiful connection to functions that we did in the previous unit. So if I want f of 4, I have 3 times 2 to the 4th. Please write down PEMDAS right here. You do the exponent before you would multiply. I saw on the last test, students who multiplied then did the exponent. That goes against order of operations. So I have to do 2 to the 4th. You don't need a calculator. That's 2, 4, 8, 16. And then 3 times 16 is 48. So we do need to be able to evaluate exponential functions. All right, questions? Anything before we continue? Anything we need to clarify in your minds? All right, then a recursive formula allows us to find any term of a geometric sequence by using the previous term. Each term is the product of the common ratio and the previous term. So I'm going to lead you through this, and hopefully this will come back to you from Algebra 1. Suppose we have a geometric sequence, 18, 36, 72, 144, 288, and so on. We call the first term u sub 1. So my first term is 18. So we would write u sub 1, and that's a subscript, is 18. My common ratio is found by taking the second term divided by the first term. So maybe write that down in case you need a refresher from 2 years ago. So my R value would be 36 divided by 18. So R is 2. Now, a recursive formula has a minimum of 2 lines. You always state your first term, and then what you do, and this is what's kind of strange, is you take your common ratio times the previous term. And the previous term would be u sub n minus 1. That just says it's the one in front of u sub n. Now, we do put this here that n has to be greater than 1. Because you can't have a subscript that's negative. That doesn't make any sense, okay? And I want it to start with 2 to give me u sub 1. So a recursive formula for us is going to have 2 rows. You have to say what's your first term, and then what do you do to the previous term to get the next one. All right, so let's look at example 6. It says you're given the, sure. U sub 1 is 2, and u sub n says take 5 times the previous term. So it says find the first 3 terms. Well, the first term is 2. Then the second term is going to be 5 times the first term. So the second term is 10. The third term is 5 times the previous term, so it's 50. So it's 2, 10, 50 are the first 3 terms. So don't let the notation bother you, okay? This u sub n equals 5 times u sub n minus 1 just means you're taking 5 times the previous term. Yeah, Davey? Because the first term is 2, and this says take 5 times the one in front of it. So if I want the second term, it's 5 times the first one. So then I got 10. Then it's 5 times the 10. So you're just taking 5 times each one. So now, an explicit formula is the one you use in general. So what that means is, like if I want the 100th term, like I can't plug 100 into the recursive one unless I know the 99th one. And that would be a major pain to have to go out 99 terms to figure out the 100th. So explicit looks like this. It's the first term times the common ratio to the n minus 1 power. So let me just write the general one. It's the first term times r to the n minus 1. Now there are exceptions to the rule here, and we're going to see our exception in example 7. It says, in 2006, there were 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing by 19.5% annually. So I want to pause here a moment. If you have growth, you take r is 1 plus that number. If it's decay or depreciation, it's 1 minus that to get the r. Let me say that again because this is important. If you have a growth that's increasing, you do 1 plus that rate as a decimal. If you have a decay or depreciation, it's 1 minus that rate as a decimal. All right, so part A says, write a model to estimate the number of people using the internet at t years, where t is the number of years after 2006. Yeah. So what we're going to do is we're going to do y equals r is going to be 1.195, and instead of it being t minus 1, we're going to put t so that in 1 year, t equals 1, that would be 1 year later. Okay, that's why we don't want the t minus 1 in there. So, do you see that's a lot of zeros to have? In that, another way to write this is you could say y equals 1.02 times 1.195t, where y is in billions. You can do that. You don't have to do that. It's your choice. But oftentimes in math, we don't want to write out like 9 zeros. So we can condense it this way. So then part B says, estimate the number of people using the internet in the year 2021. Well, T is the number of years since 2006. So we're going to take 2021 minus 2006. How many years is that? 15. So then watch. And I'm going to use the condensed formula. So let me give you a moment. So go ahead and take your 1.02 times 1.195 to the 15th power. That would be 15 years later. And I'm getting 14.76 billion people.